Yeah, thank you all for being here this morning, and thanks to Organize for the opportunity given to us to present this work on quantum error correction. So I'm just going to start by explaining what quantum error correction is. So traditionally, at quantum error correction, you have your quantum state and you want to encode it to a higher dimensional system such that it is noise robust in the sense that I can do, after some noise occurs on this higher dimensional system where I encode my state, then I can do some decoding where I measure and then I can infer if there's any error occurred and then do some correction to recover my original state psi. So just one example, you can encode a 1 qubit to this array of qubits represented by these white dots. And then I do this measurements um, and I do some classical processing to determine whether there's an error or not and try to correct it. So this one simple example is this so-called toric code. So I have this L by L lattice, and I put my qubits on the edges, represented by these white circles. And then I wrap them around this donut-shaped object called a torus. And I do this 4 qubit Z measurements on the faces and 4 qubit X measurements on the edges. And if you notice, all of these measurements commute because the Z's and the X measurements coincides on 2 qubits. And then I just take these Z and X observables and I can create what is called the stabilizer group, where a group, an abelian group where all the elements commute. And I can construct my code space by taking all n qubit states where if I do measurements on these 4 qubits, I'm going to get a +1. So that's how I define my code space. Um, so all the measurement here commute, as I mentioned. That's how I get my code space. And how do we correct errors? Whether an error can be corrected or not has been figured out, worked out by Neil and Flam about 30 years ago or so. So if I have this set of errors, E sub E, um, then I can determine whether these errors can be corrected by a given code by taking those bases of the code space represented by that I bar, and whenever this condition or errors can be corrected if and only if this condition is satisfied, which kind of like basically in a very high level means that the errors kind of still preserve the orthogonality between states in my code space. But you don't always need to do commuting measurements. You can do non-commuting measurements, and by doing that, you get what is called the subsystem code. And this is one example of it, which is called the Gitaev's honeycomb model, which was proposed about like 20 years ago. So in this case, instead of having this square lattices, I have this hexagonal lattice. And then I put my qubits on the vertices and I wrap that around that donut-shaped object torus. Now what the difference here is, I put colors on the faces and on the edges. My apologies if that's a little bit hard to see. But the point here is that the color of each edge that connects um, the edge that connects two faces of the same color have the same color as those two faces, right? So this red, red, then you get the red edge there. And I define my measurements on the edges, and so I only have 2 qubit measurements, right? The green one are 2x's, the y's are reds, and the z's are the blues. And obviously, like this don't commute, right? So if I have like xx there or xx there and zz there, then they don't commute. But you can still do error correction this way. I can define my stabilizers as these faces. So the green ones are the z's, the red ones are the x's, and the blue ones are the y's. Um, yeah, and I can basically measure this 6 qubit stabilizers by just doing three 2 qubit measurements on the edges that surrounds it with the same Pauli observable flavor. But unfortunately, it you can show that this cannot encode any logical qubit, which is kind of like, okay, so it's kind of like useless, but not really. And I will tell you why in a little bit. Um, okay, yeah. So just a little some facts. So since you have a non-commuting measurement, so you have to construct like a schedule on how to measure to get your error syndromes, um, and you still have a fixed code space here. And there's also necessary sufficient condition by Cripps, Laflamme, and Pauling. And why we care about subsystem code is that because you can use this um, in a protocol to do universal photon computation in a protocol called the code switching. And it has some connection to quantum contextuality. If you're interested, like just a quick advertisement on this paper right here. But I'm not going to talk about that in this talk. Um, okay, so it seems that it's useless here. This code is useless because you cannot code anything. But 20 years later, it turns out that you can actually encode something in a way that is in a non-traditional way. And that was figured out. Hastings somehow figured that out. Was this like 4 years ago? Basically, what they figure out is that okay, so the measurement don't commute. So you have to construct like a schedule, a sequence on how you want to measure stuff. And what they did is that okay, I'm going to measure all the green edges and then the red edges and then the blue ones and then do that over and over again. And by doing that, what they notice is that okay, so now I have a different stabilizer group after I measure each of these set of measurements. So it kind of like so your code spaces basically changes every time you measure this green, red, blue checks. And what they found is that you can actually encode two logical qubits in the same code by noticing that by relaxing the requirement that you have a fixed code space. Yeah, so that's the rounds. And yeah, basically, as I mentioned, if I measure the green checks, like the green two-qubit measurements, then I'm basically measuring all the red stabilizers, and the same with the all the other rounds. Um, okay, yeah, so that's what I just mentioned. So if you see this code, so these are basically just the same code. I'm just kind of like flattening them. So this is one hexagon, but we can reshape this. Yeah, if you see this code as a subsystem code, you cannot really encode anything. But if you see this dynamically, so this is kind of like the first round. So you have this kind of like logical operator, and then logical operator changes every time you do like this two-qubit measurements, and you can encode two dynamical logical qubits. There has been a lot of work on dynamical codes since then. QLDPC variants, CSS variants, hyper on dynamical code on hyperbolic surfaces where you can encode large number of logical qubits and so on. There has also been implementations or experimental implementations by Google just last year, also from this group. Um, and yeah, they're showing like quite promising or comparable performance to like static codes. Right. So this is just a summary of what I've been mentioning. So in a subspace code, like all the check measurements commute in the subsystem, it doesn't commute, but you still have a fixed code space. And in dynamical code, you have non-commuting measurements, and you have this sequence of codes that you get by measuring this non-commuting measurements. Um, so yeah, in the subspace code, you have the nil-Flam condition to determine if whether errors can be corrected, and you have the Cripps condition for subsystem code to determine that. But the dynamical code part of that is kind of missing. Like it's kind of weird because like now you have a sequence of code space instead of just a single code space. So can I use this nil-Flam condition? Can I use a Cripps condition? Because it's not um, um, super clear at this point. Um, so that's basically like our motivating question on this that motivates this project. Um, yeah, necessary and sufficient condition, and we also like trying to think probably there's because all of these codes seems to be very different. So is there like one unifying framework where all of them can be captured in this one big picture? Um, yeah, so basically yeah, that's what I just mentioned. And in addition, like we also thought about non-Markovian noise. I'm going to talk a little bit more about that later. And how is there like a systematic way to construct these dynamical codes? Yeah, so this is kind of like the landscapes. You start from subspace code, subsystem code, dynamical code. Is there like something else that captures everything else beyond that? Right. So yeah. So I'm gonna first talk about the framework that we use, and then I'm gonna show you the answer to the question that I had earlier. That this missing piece on how you determine whether errors can be corrected or not in dynamical codes. And I'm gonna talk a little bit about how to systematically construct dynamical codes using the optimization route. And I'm gonna um, yeah close on. Right. So traditionally, this is the picture, the error correction picture. You encode something and then some error occurs, then you do some decoding, you try to correct them. But a more comprehensive picture is that, in the dynamical codes, like you do more things in between, right? So that's what kind of like how we came up with this framework. So we add not this object between the encoder and decoder, which we call the interrogator, which is this blue object. So that's going to represent whatever you want to do between encoding and recovery or decoding. So I'm using recovery and decoding interchangeably here, but they basically mean the same thing for the purpose of this talk. Yeah, so this is our archive paper where we on this work. So I'm just going to explain now the objects in this. Okay, so I should call this is the strategic code, right? So the whole thing here. I'm going to explain like each of the objects there. So first, I have like this noise, and we keep this general so that the noise can be correlated from the one step to the next. And that's why we have this wire going from noise at time 0 and time 1. Um, and this whole thing is what we call the strategic code. So it consists of an encoder and whatever you do after that before the recovery stage. Um, so I'm just gonna ignore the encoder here for simplicity. So I'm just going to start with some code state. So I say I do encoding, and then I map my side to this logical state sidebar. So I'm just going to start with that. We can conveniently represent this entire object, like this sequence of operation, along with the initial code state as this one big vector, which we call the temporal code state. And that's basically, I'm just going to yank all the wires and make it look like that. Then I can have like this one big quantum state. Um, I should say it's not really a state because it's not necessary. It's not normalized. Um, and each of the state have this subscript m here, and that's mainly because we do allow this propagation of classical information from one step to the next, represented by this double wire. So there is some dependency on like this classical memory state, and that's represented by this m here. Um, Yeah, so by representing the initial state and the interrogator that way, I can think of this noise as a linear map on this temporal code state. So it's not just a linear map, it's a completely positive map. So it will admit this cross representation. And yeah, we call this higher order cross representation because this is kind of like a special case of a completely positive map. It has to satisfy some conditions, which I'm going to talk about a little bit later on. So basically, this noise E will act on this temporal code state this way, which is like this familiar form that you always see when you work with quantum channels or CPTP maps. Yeah, so this is basically a formalism that's called quantum comb or quantum strategy or process tensor. They all mean the same thing to me, just different authors call them different things. There's the citations there. Right, so what does it mean for error to be corrected in this picture? So okay, I have this initial code space, and then I have this interrogator, like this operation that I do, and then some a recovery. So what I consider this error to be corrected is that when I put some state sidebar, um, there exists some recovery map which will depend on the classical memory state. So you could think this classical memory as something that you feed into your recovery channel, which are just information about errors that had occurred if you do some measurements between the recovery and the encoding. Then what I want is that for this to output the same state psi or something proportional to it if I don't have trace preserving operations there. Right. So using those kind of like framework, now I can come to the necessary and sufficient condition um, on this picture, right? So this will apply to the dynamical code. In the dynamical code, you just replace this interrogator with this sequence of check measurements, but you could do like something more general. You could do like gates here or whatever. Um, so this looks very similar if you're familiar with the Nila-Flum condition, or actually I have it down there. So I just took the sandwich of this kind of like this higher order cross error cross operator and sandwich it with the temporal code state with different initial um, uh, code space basis, this I bar and J bar, and we get something very similar. So um, basically, like whatever this operation that I do with this interrogator and the errors, the resulting state that I get out of that is going to preserve this orthogonality between um, the initial information that I put into it, right? And now it has this additional dependency on M because I have like this memory, classical memory going between the operations, but essentially they're all the same. And if I just ignore the interrogator here, I'm going to recover the initial, this Nila-Flum condition from 30 years back. Um, and yeah, because now you get like this the traditional picture of error correction. Let's see, okay. All right, so let me just go through the outline of a proof real quick. I don't think I'm gonna go into details, but yeah, feel free to come and talk to me afterwards if you would like to know more. Um, So basically, the idea here is that to show that if the strategic code corrects this noise E, then this condition is going to be satisfied. Is basically I'm going to use the fact that this recovery channel. So remember, if I can correct the noise E, there exists this. I can always there exists this recovery channel for each M, um, and it's going to output like something proportional to the input state, right? And so that's the reason why I have this kind of like a constant m. Um, and basically, yes, because this is a CPTP map. I think I'm missing a step there, but uh, yeah. Anyway, so if I expand this, and I'm going to get something like that, right? So if you remember, like that's the TM, but I'm gonna like I can put anything there, and then I can expand this as this E like in this cross form, and this R also has some cross operators. Yeah, just that. So one side of that is gonna look like this guy right here, um, and I can show like this basically whatever I put here is going to map you back to the initial code space Q0 um, up to some constant. Um, so now I can write this term that way by putting this constants gamma in, and then I can get like this kind of form because now it's gonna reduce to that, and this guy's orthogonal. Um, the the other way around, it's okay. So this is very simplified. Um, so the idea is that can show for each m this going to this is basically a Hermitian operator, um, which are indexed by this E and E prime. So you can diagonalize it um, this way. So I diagonalize this matrix to this diagonal matrix. So if this E and E prime are non-equal, this it's going to be zero. So it's just on the diagonal. And I can use the unitary to diagonalize that. So it's just like spectral decomposition kind of thing. Um, and I can construct a different form of cross operator of my errors, um, and then kind of like use that as the recovery channel. Yeah, sorry, it's kind of like very high level thing, but kind of like the idea is that like you want to notice that this is permission, so you can kind of like use this equivalence between cross operators of the noise linear map and construct a different cross operator. We also have a different condition in the information theoretic form, which kind of like more intuitive in a way. So in this setting, um, I want to put like one half of a maximally entangled state into like this whole process, and the other half goes through. And okay, I'm not going to go through everything here, but the idea is that so this reference system, this R system, cannot be entangled whatsoever with the ancillary systems that I use to perform this operation, plus the noise environment E. So that's kind of like the intuition behind this. But we can formulate in using different entropic quantities. Yeah. Lastly, I'm just going to go through this real quick. So I can express this entire thing basically in this positive operator form with this tensor product structure. Um, since they're positive semi-definite operators, so there's this very huge um, body of literature on semi-definite optimization. So that's basically what we did here. So we maximize this. We use this iteration of semi-definite programs. And that's like we have some results like construction of dynamical codes using this method in this paper. I'm not going to go through in detail, but you can talk to me later or read the paper. Oh yeah, and we also came up with approximate dynamical quantum error correction condition, which is that guy right there. Okay, so that's pretty much it. So yeah, just going back to like this exploration pathway of error correcting code. So we can first have this subspace code, all commuting checks, fixed subspace, and then you can have subsystem code, um, non-commuting measurements, still fixed subspace, dynamical codes, non-commuting measurements. Now you can have dynamical subspace that changes over time. And I don't know. The last thing probably you could think of this as you can do things adaptively in the sense that if I measure something, then I can decide which subspace I want to go to. So that's in principle possible in our framework, and we can check whether errors can be corrected using the error correction condition that I've showed you earlier. But we still look for a concrete adaptive code, and in which case it could be useful. Um, so that's one open question. That's yes, it's probably listed here somewhere. Yeah, and we'll also look into fundamental limitations of quantum error correction and fault-tolerant computation using the space-time picture, and cases where adaptively helps, which I just mentioned just now, and systematic construction of not just error correction but fault-tolerant protocols, probably using optimization means or like other kinds of other means as well. Probably we could also like construct this one big framework that consists all of error suppression and error control methods, including error mitigation and so on and so forth. And lastly, I'm just gonna want to thank my collaborators. I think Kishore's sitting right here, and yeah, Milagu from NT. And that's it. Thank you.
Thank you, Andrew. Do we have questions? Yeah, go ahead, sir.
not necessarily. So you could just you could do measurements, but basically how we model this. Oh, okay, so that should be double wire, but yeah, each of the C1, C2, and C3 are quantum instruments, and what that basically means is that you have like this family of completely positive operators. If you sum them up, you get a CPTP map. So it's basically yeah, just a general completely positive map. So you could do. Sorry. Oh. Uh, yes. Yeah, it's basically that. So you could think of I'm going to just like um, reshape this thing into that, and then I put unnormalized maximally entangled state here, and then yeah, like the other half is just goes through. It's kind of like of this. Okay, so if you forget about this part, um, you can think of this as this Choi matrix of this object.
Maybe one last question.
Um, I think it will be okay. I'm not entirely sure on this, but I think if everything's Clifford or like just stabilizer circuit, stabilizer measurements plus Clifford gates, I think it's gonna be a stabilizer state. I need to double check on that though, but great question. Yeah. Mhm. Ah, yeah, it could be anything basically. So I can take this as an encoder for like I don't know, like surface code or toric code or yeah, and then I do stuff after that. Uh, sure, yeah. Um, yeah, I don't know like what that will look like. I mean, you could certainly always think of like temporally correlated analog of defacing or polarizing noise. You mean hybrid of classical and quantum codes? Um, yeah, there are some work on this. Yeah, like a code which can where you can encode both classical and quantum information, but we have not really explored that. But I'm pretty sure that will definitely fit here. You can just take this encoder to be the encoder for that particular code. I don't know, like it will probably be useful in some cases, but yeah, we haven't explored that. But yeah, great point.